Hello, everyone, and welcome to tonight's Global AI on Virtual Tour event. So tonight we've reached Norway and Oslo. So we will have 3 interesting presentations tonight. My name is Håkan Silverhagel, and I will be the host for this evening. So the agenda for tonight is, first we will have a presentation about Azure Personalizer with Monica Beate Tvedt. And then our second presentation is about Explainable AI, how you can make AI responsible, by Alise Danielle Midtfjord. And then our last presentation is Reinforcement Learning with Pac-Man with Manu Gopinathan Malte Loller-Andersen. But before we start off our evening, I have a couple of announcements here from the global AI community. So first off is I would like to present to you that in October we will have a live event called Global AI Community on Virtual Tour, which is a 30-hour marathon of AI presentations going all around the world. So we'll start in Auckland and then we'll finish up in Seattle. So if you're interested in sharing something that you are passionate about, you can fill in our CFP, our call for papers. So you can reach that on the live.globalai.community address. And secondly, I would also like to inform you that we have a bi-weekly show called AI Talks Live. So our next event is tomorrow. So we will have Charles Sterling as a guest, and he will talk about what is new and exciting with AI Builder. And also, I'm happy to announce that we also got a gift here from Microsoft. So for all of our viewers, you can get an exclusive Azure Heroes Some Learning badge. So all you need to do is to scan the QR code with your mobile phone, or you can go to aka.ms/Azure Heroes badge to retrieve this to your virtual wallet. And we will also show this at the end of the evening, so that if you don't catch this QR code right now, you can do that by the end of this event. And if you have any questions or any comments throughout the night, you can type them in to the YouTube chat. And then after each presentation, I will present the questions to the speaker, and we will have a short Q&A session. So with that said, I would like to add our first speaker here to the stream. So first speaker is Monica Tvedt. She is an Oslo-based hands-on technology director with a strong passion for .NET and Azure development. She has over 20 years of experience within the Microsoft stack. Regardless, it can be mobile development with Xamarin or building web applications using the .NET Core framework and Azure. She tries to encourage knowledge sharing both at work and also in her local community. And she does this by arranging both in-house meetups and lab exercises, or by organizing gatherings in her local tech community. She is also leading Norway's largest Xamarin community group, the Oslo Xamarin Meetup, and she is the owner of multiple academy training programs. She provides workshop, tech talks, and customer training for clients, meetups, and conferences. So welcome, Monica. We're really happy to have you here.
Thank you, Håkan. Nice to be here.
So can you share a couple of words about what you will present tonight?
So today I will talk about a new AI award-winning service from Azure, the Personalizer, which helps one to improve the user experience and the user satisfaction with real-time learning and decision-making. So we will go a bit more into details in a few minutes and see how we can make use of this new service.
Yep, that sounds very interesting here. So I will add your presentation here to the stream.
Yes.
And then the stage is yours, Monica.
Thank you. Yes, so hi and welcome to our first virtual session. I will be talking and giving you a short introduction to the Azure Personalizer. First off, I hope you all had a great day at work, perhaps learned a thing or two. So I haven't done a virtual session before, so this will be a new experience for me also, not talking directly to you all. So I won't be able to ask you any questions or answer your questions as we go, but we will have some time for Q&A afterwards. So, as Håkan mentioned, my name is Monica. I'm the Technology Director at Forte Digital, a consultant firm specializing in AI, machine learning, .NET, and Azure development. And he also mentioned that I love to encourage knowledge sharing, both at my work and by attending and arranging tech community meetups. And the reason why I love doing this is not only that I truly believe in the power of sharing knowledge, but it also kind of forces me to keep on learning myself and exploring new services as they become available, like, for instance, this Azure Personalizer. So by doing this, it forced me to sit down and start learning about how to use it and starting to think about how I can use this in my own projects, both my private ones and those at work. So today we'll be talking about the Azure Personalizer. It's an award-winning AI service from Azure, and we'll be looking roughly, let's say, not too deep into the details, because those you can read on later on Microsoft's documentation pages. But basically, Azure Personalizer is a cloud-based API service that allows your client applications to choose the best experience to show to users, learning from their real-time behavior. So the service itself aims to provide what we call a content recommendation functionality that can be implemented without having the machine learning expertise. So Azure Personalizer actually then has a huge potential because it uses one of the most powerful machine learning techniques, reinforcement learning, which you also will be hearing more about in the next upcoming sessions. So what Personalizer does is it monitors the user behavior and reports a reward, or you can call it a punishment score, back to Personalizer to improve the ability to select the best user experience based on the context and the information it receives. So before we go into explaining how it works and how to train it, we will create it so we can make use of it. And since the Azure Personalizer is a cloud-based service, we will need to create and access the service online through the Azure portal. And to be able to do this, you will need an Azure account, or you can create one for free. Me, myself, I will be using a pay-as-you-go subscription, but I think many of you who are watching may have a Visual Studio subscription at work that you can use, because that has some free Azure credits that you can use on Azure. And depending on the subscription level, I think it ranges from around $50 to $150 a month. So for the slides, I have created some screenshots explaining what to do and how to fill it out if you want to have a look at it later on. But we'll also go through it on the Azure portal now, so you can see how it's done. So let's get going. So now you see my screen. I have just entered the portal.azure.com, logged in. And first off, we will start by searching for the Azure Personalizer service. So just start to enter, and you will get it as the first option on you see underneath the marketplace. you click that. And you will see the form that we need to fill out to create our Personalizer service. So after filling out the necessary form, Azure will then create our API, the initial model, and the learning policy for the model. And this can take up to 10 minutes, depending on the service and how you set it up. So I have, of course, created one last night. I've been cheating. So when this is created, when you click create, you will get a confirmation stating your resource is set up and ready to go. And it will look like what you see here on your right-hand side. So first, you see that your deployment is underway. And when it's done, you just click the service name. So I will just show you. And then you will see your service like this. I called my service my Personalizer learning loop. And if you see on the left-hand side, we have many different options. You have the configuration where you can set up how the Personalizer will do its reward. So you can see here, how long should it wait before it sets a default value if it asks for a ranking and doesn't give a reward. You have exploration that we'll look into. You have also model and learning settings. This is nice to be aware of because when you do your own experimentations, you often need to go in here and clear your data. So you can start all over again and learning your model. Also, we will have a look later on the keys and endpoints, because these are the settings that we will need to paste into our .NET Core applications later on. Let me start by looking at the configuration. So I mentioned the exploration. Here we have the opportunity to configure exploration to allow the learning loop to adapt. And this way, Personalizer is able to discover new patterns and adapt to user behavior change over time by exploring alternatives instead of just using the trained model prediction. And the default here is set to 20%. And often I've learned that when you create like data-driven applications, it is not creative. So you just get a trained model, and prediction is always based on what you have done before. So it's missing like the creative human touch of exploring new interests or new ways of using the application. But this actually covers that need. So now you have both the exploration, but also the learning by what the user previously has been doing. So when the Azure Personalizer is set up, as we have done now, it was quite an easy process. Just filled out the form and clicked create. But things get much more trickier when it comes to actually training the model. So you will not be able to succeed without some basic coding skills. But I have created, and we have all the code already implemented. So it's easier for you to just download the code and have a look at it later on and get to be more familiar with the actual implementation. But basically, it follows these 3 steps when it comes to using the Azure Personalization service. So a bit much going on these slides, but you can see I have tried to show it as in the upper left-hand side, you see the user, which will be using your website. And then you see the API calls on the right-hand side. First, it calls the rank API, then the rank response gives you back a ranking, and the user again sends a reward back. So let me go more into details. So first, calling rank API is done by sending a list of, in this case, different possible page layouts and the user context. And then the goal is trying to achieve the best user experience. Personalizer then decides whether to exploit the current model, as we just talked about, the past learning, or explore new choices, which in this case will be about 20% of all the rank API calls, since that was the default value. The ranking result is then sent back, or first to the event hub, actually, because the event hub is used for sending and receiving the messages. The rank API then returns the top ranked items back to the client. And the client first has a responsibility of then showing, or at least handling the top ranked item, for instance, showing the top ranked layout, and then monitoring the user behavior. I mean, was it a successful match? Did we manage to get the user feedback that we wanted? Did it do what we wanted the user to do? And after we have done the evaluation of that, we send a reward back between 0 and 1 to the reward API. When the personalizer then receives the reward is again sent using Event Hub, and the rank and the given reward are then correlated. So the AI model is updated based on the correlation model or the results, and then the inference engine is updated with the new model. So we will show this in action, so it will be easier to understand. It's not that difficult. So for this demo, I've chosen to use one of the samples that you can find on the Azure sample GitHub repository. So it's called I think it's underneath the Azure Personalizer GitHub repository. And this, as I said, this demo already had all the code for the training model implemented. And we will take a closer look at it. So here I just have stated for reference later on, so you can see what you will be needing to run the demo on your laptop or your computer. The solution is a .NET Core MVC applications. You will need .NET Core 2.2 or higher, preferably Visual Studio 2019. The Azure Personalizer instance, which is the one we just created on the portal. And you can use or clone the repository either by doing it through the GitHub portal, or as I've been show you here, through a terminal using the git clone command. And when all the samples are downloaded, we will navigate back to our project folder to be able to store the user secret. The user secret in this case is the API key that we found on the Azure portal. I will show you. And I will be, it's many different ways of storing a user secret. You can do it using the Azure Key Vault. For this demo, I've used the .NET Core CLI and just stored it as a user secret. I can show you how this is done. If you want to take this certification, Azure Fundamentals, the this is one of the questions, so a tip. It's for the certifications, you need to know a lot of the different commands and how to do it, both through the Azure portal, but also through a command line window. So here is, you see my, let me just hide some of these windows. Here is my terminal. So I've navigated through to the project, and I'm here using the .NET users secrets set, personalization API key, and the key is the one we found on the Azure portal, and the keys and endpoint here. So it says key 1, key 2. I use the key 1. And also the endpoint we will copy and paste into our solution now. So let's close this. We don't need this anymore. So let's open Visual Studio. So let me see if you can see this. I'm guessing Håkon will give me a heads up if the font size is too small to see. So you see on the left-hand side in the root folder, app settings. When you open this, you see it has already the personalization endpoint entered with a default value. So here you need to copy the API URL that we found on the portal and paste it in here. So then we are ready to run our demo. As I mentioned, that what we do when training the personalization service is that we give it the different kind of actions we want it to choose from, or the different kind of, in this instance, the different kind of layouts and the context, right? So this is a web page that offers travel packages, renting cars, so everything you need for your holiday. And it wants to, when you have bought or selected a holiday and it's added to your shopping chart, you go to the checkout or you start the checkout process. It often ends in user aborting and not completing the purchase. So what this company wants to do is to have more people actually buying the packages that they have selected and the checkout process that they have started on. So to reach that business goal, they have created a set of 24 different layouts. So it's when you actually want to complete the purchase, they can display the layout in 24 different ways. So it's a JSON, which contains some values called features. So here you can see it can select a variety of different images to display on the page. It has various different layouts it can choose from. It has different tone of font. So one font is more casual and another font is more formal. It has different colors for the buttons. In this case, it's an orange or a blue one. So then it sends all these different options to Azure Personalizer together with a set of context features. So let's see this in action. I will just start it again. So So welcome to our holiday agency. So this is the page. I am, as a user, have now chosen a vacation, a boating trip that includes dinner and breakfast. And I want to go to the checkout. So this is what is shown me. It's a description page that says something about the vacation package I have chosen. Has an image. It has a confirm purchase button, or I have a save for later. Perhaps I'm in a hurry and I cannot buy the package right now. I just have created everything and set it up, and I will go back and actually do the purchase later on this evening. Also underneath, it has an overview of, let's say, the cost, what the package includes, and some new, what we can do nearby. So this is one of the layout alternatives. We have chosen an image. It has a layout where the button is right underneath the image. You have the save for later option, and then it has more details underneath in a certain order. So first the discover, then the cost, and then what the packages includes, right? So now I've opened this, and the Azure Personalizer has actually already started to work. Just to be able to illustrate what is actually happening, you can see up in the right-hand corner, it says 0.5 conversion reward. So this is the score that we will be sending back to Azure Personalizer to begin to train our model. And for this application, I have chosen some reward scores. One is if the user instantly clicks the confirm purchase button. 0.5 is the lowest one if I click and actually buy it. If I decide, which I will do now, to save it for later, I will only send a 0.2 because I didn't actually get the user to buy it, so it's not a success. If the user didn't put save it for later and didn't buy it, but just left the page, I send 0. And that is also one of the configuration in Azure portal that you can set, that if one don't receive a reward back, then after 10 minutes, it sets the reward for you to 0. So let's see how this actually is done, both the request and the response. So this is what happens behind the scenes. So you see up here in the right-hand corner, you have some, as I said, first you provide the service with a list of different layouts or actions, and then also something that says or describes the context. So here we send 3 different features. We have a trip type. So if the user has chosen a personal or a business kind of trip, or what the intent of the trip is. You have the traveler history. So if it's normally they buy something within the economy class, or if it's more of a luxury trip, which device they're on, correct? And underneath, you see how the JSON format is actually structured. So you have the context features, you see device, the trip type, the traveler history. So that is the one part, correct? The second one was the possible actions that we need to send. This is just visualizing, so it's more easy to see. I will show you also how the actual JSON looks. So here you see it's the different layouts that we provide. It has a different kind of orders or order for the boxes underneath the image. You have different kind of images, one with a sea. I think he's paddling on a beach, and the tone of voice, as I mentioned, more a casual kind of font and a formal one. And the buy button itself, one that is blue and more below, you know, the information boxes you see, and one that is orange, which is right beneath the image. So perhaps if you see the confirm purchase button right away, you will click it. If it's more hidden underneath, perhaps you will lose more customers during the process. Who knows? The actually JSON, as you see, is the one that I also showed you in the Visual Studio right behind us, as you see. So these are the two JSON lists that they are actually sending to the Rank API. So, and what you get in return, okay, let's just try a new one. Business, luxury. See if it's anything different. So we have just started to train our model, meaning it's not that big variances in what we do. So yeah, so here it tries to mix up the information boxes. So we can see on, let me hide this, on the right-hand side, the API response. So this is the important bit, because when you have sent to the Rank API, you get back this response. And it states the reward action ID, which is 19, which is the layout we want to use. So then we put up the layout we see. And underneath, you can also see the ranking for the different kind of layouts. And underneath, you can also find out if it used a learning based on previously user behavior, or if it's in exploring mode. So this way, we can start by training the model. Let's say, save for later. Go to new checkout. We confirm the purchase, and so on and so on. And so normally we would want, or we need to do this like a lot of, let's say 5,000-10,000 times before the model starts to learn from the user behavior. So we won't get instant result right now, but we can show you how it's learning. So normally it starts taking in all the user engagement rewards and become better and better at learning what or which layout it should display to better making a successful purchase. So now it's an average of 0.8. I've been using this quite a bit, so it's already started to learn. So that was the quick intro. You can afterwards, or later on, or tomorrow, or the next weekend, go into and have a better or more thorough look at how the rank request is built up. It's quite easy. It's just a few lines of code. And also how the reward request is done. And all this is available as long as you actually include the, here you can see, the Microsoft Azure Cognitive Services Personalizer. Then you have those actions and methods and calling available. So, yes. So why should you use Personalizer anywhere? So you should use Personalizer in, or you can, in any situation where your application needs to select the correct action or content, as we just did, in order to make the user experience better. So, and one of the most important things to remember is that why do you want to do this? it is actually to achieve better business results or improve productivity. So when one chooses how to do the reward scoring, it should back up the business goals you're trying to achieve. So according to HubSpot, actually, I think it was 74% of online consumers was shown to be quite frustrated when they were displayed items they were not interested in buy. And they also found that if you had a more of a personalized approach with call to actions, like the ones we had with complete your purchase or buy this right now, it actually showed an increase to 43% higher view to submission rate than when the call to action were the same for every visitor. So you can take streaming platforms, for instance. You have like YouTube and Netflix, Spotify, they're all great at this. Also, the more advanced e-commerce sites we see coming up the last couple of years. So they are all delivering relevant and personalized and intelligent experiences for the users. So it's all about offering each of your customer a unique experience so they can begin to feel both known and understood. And by doing so, they start spending more of their time on your site, and they begin to trust your brand more and begin to be more engaged. And they are also shown that it's much cheaper just trying to retain the customer you already have and gain more value from them than trying to gain a new customer. So this ultimately leads to a great return of investment, and it reduces, as I said, the threat of losing a customer to a competitor that perhaps has an even better tailored website. And so to be able to do this, I think the best thing is to just go back and try it for yourself. I've just started to learn this, and I read some of the documentation on Microsoft's pages, but they have a lot more in-depth details when it comes to scaling, performance, and as you know, using Azure Personalizer, it's best fit to a smaller subset of options or to choose from. If you have larger sets of different kind of actions you want to choose from, you should first reduce it to a minor subset, which you again then send to the Azure Personalization service. So to be able to do this, on the last slide, I've created a small list of resources just to get you going. So where the Azure portal is, where you can find all the coding samples and the documentations, which is really good, that will guide you through all the different steps and more in-depth information on customization. So thank you. That was that.
Okay, so thank you very much, Monica. This was really interesting.
Yeah.
We have, yes.
Yeah, it's a lot of details. So it's like when you start using it and understand it, because it's quite easy actually. But then I think the difficult part was, trying to figure out which business goals do you want to achieve. That is one thing, but actually doing the right rewarding the scores and how to, so it's more of the business logic, I think, will be what one spends most time on trying to figure out. So, but it's like with all the different services on Azure, it's extremely easy to use. I mean, we have seen, previously on different kind of services, cognitive services like the custom vision and just image recognition, and it's so easy. So we are like spoiled. Developers today are spoiled. Yes.
Yeah, we have a couple of questions here for you, Monica. So one first question here is this a new service, or how long has it been in existing?
I heard of it, I think it was last year. So it won a couple of like rewards last year, if I'm not mistaken. So and myself, I just started using it, I think, this winter. So when I had a chat with you early this year, it was my first meeting with it. So, and I know that when it was in preview some time back, last year, I think it were in preview, and it had some issues regarding getting a good trained model. So it had some limitations, especially using the free tier setting, etc. But now it's much better. And it's important to remember that when you do the configuration on the Azure portal site, to actually do different kind of settings when you are in debug and when you're in production. So I just remember that I forgot to do this for the demo, because then I should have put like update the model, after it's been trained and have gotten the rewards, it should update itself. So now it didn't get updated until every 10 minutes, meaning it wasn't able to show what it learned when I did when I purchased several times. So remember that for you who wants to try this afterwards.
Yeah, it touches a little bit about the next question here. So what is the actual cost of using the personalizer? And do you have a development mode and a production mode? And what are the different costs of that?
Yeah, they have this free tier that you can use. And I used myself now the S0, which is, I'm not sure how much it will cost me. I will figure it out. And the most important thing now is I need to remember afterwards to delete what I just set up. So I've forgotten that in the previous workshops we've had, and I got a surprise bill from Azure. So I haven't used this in production myself yet on our projects, so I wouldn't say. But I know that on Microsoft's documentation pages, they have this formula stated where you very easily can calculate what it will cost you. So it says something about the data and the usage. So I can post that link afterwards where you can do the actual calculation.
And then the last two questions here. You said that some coding skills is necessary to run this, but how much machine learning skills or do you need to know beforehand?
As I started out with, you don't need machine learning expertise at all to be able to just use Personalizer service. But you can, let me see if I have it here, but you can export the model and the training. I think it's here, but I'm not sharing. Yes, but so at the Azure portal, you can go to the model and learning settings, and there you can export the model itself and the learning settings. And there you actually get like more things that I don't know how to read. But the Azure Personalizer is more for those who do not have the machine learning expertise. I think I would use some of the other services myself if one would do or want to do something custom. Yeah.
And then finally here, how can people contact you if they have further questions or comments?
All over. No, it's on LinkedIn, or send me a message on Facebook, or Yes. So probably LinkedIn would be the best one because I'm always there and getting the notifications. So I can also give you the link to the LinkedIn afterwards.
Yes. Okay, so then I thank you so much for your presentation, Monica.
Yeah, thank you. It was a new experience. So
and then I will introduce here our next speaker, Alise Danielle Midtfjord.
Hi, Håkan. Hi, everyone.
Hello. So Alise, she's a PhD candidate at the University of Oslo, where she's working with developing machine learning methods for high-risk engineering applications. Her passion for artificial intelligence was developed through her Master of Science studies in physics, where she used AI in conjunction with cancer research, and her experience working with new technologies at Accenture. So an important topic for Alise is working towards creating explainable artificial intelligence, or XAI, which is necessary in order to address the challenges rising with the rapid growth of artificial intelligence. So that sounds very interesting, Alise. So what will you specifically talk about in your presentation?
Yeah, especially what you just said, I'm going to talk about explainable artificial intelligence. And that is basically a method or methods how to make artificial intelligence more ethical, more transparent, more understandable, and yes, open up those black box algorithms that we are always talking about.
Okay, so I'm looking really forward here to hearing your talk here. So I will add your presentation to the stream, and then the stage is yours.
Great, thank you, Håkan, and thank you, Monica, for a great presentation about Azure Personalizer. It was really interesting. As Håkan said, I'm going to talk about explainable artificial intelligence. And of course, I would prefer to see you all in person as I meet you. I always like to meet people that are passionate about artificial intelligence, but I guess virtually will be good this time as well. Earlier, if you have any questions, you can just put it into the YouTube channel on the chat there, and we can take it in the end. And before I'm going to jump into explaining what explainable artificial intelligence is, I'm going to ask you guys a few questions to get you into the mindset, and you can just kind of answer them in your head and make what you think is right and not right. So I'm going to start doing that. So first question, did you guys know that if there is a car accident, women actually has a 47% higher chance of getting seriously damaged or injured in the accident than men? And do you think it's fair that the reason for this is not that we are like weaker or more weirdly shaped or anything, but the reason for this is that when they created the cars or designed the cars, they actually did not bother to test the cars on female-shaped dummies. They only tested it on male-shaped dummies. So yeah, do you think that is fair? And I guess some of you also have started using these voice assistants. We have, for example, Siri, or we have Google Voice Assistant. And did you guys know that actually these assistants have a 70% higher chance of understanding a male's voice than a female's voice? So that means for you women out there, if you're kind of sitting in your car trying to speak to your phone, maybe your GPS or something, and you have maybe like a boyfriend or husband next to you, you should definitely let him do the talking because it's much higher chance that he will understand him than you. And do you think it is fair that the reason for this, that we don't have an equally good product, is because they mainly trained the algorithms on data from male voices, actually? And in the end, in the United States, people often want jobs, so they apply for job interviews. And did you know that if you have a foreign sounding name, you actually have a 50% less chance of getting a job interview? 50% less chance. Do you think it is fair that you should get a job interview not based on how good you are, how skilled you are, but mainly on how, but a good reason is how your name sounds? If you ended up answering no to any of these questions, or maybe all of them, you already know some good reasons why we had to not focus only on creating artificial intelligence, but why we had to focus on creating explainable artificial intelligence. So a little bit what I'm going to get through on this presentation. I'm going to take a small introduction to the topic before I'm going to talk about these black box systems that we all hear so much about. And what is the opposite of this? That is namely explainable artificial intelligence. And how does it work? I'm going to tell you about why do we need explainable artificial intelligence. And then I'm going to take you through my favorite method of creating this, namely called layer-wise relevance propagation, or LRP. And I'm going to finish off with some examples how LRP are used today. So, some introduction. I guess you all that are here know that artificial intelligence and the use of it is growing so fast right now. Actually, I just read a report from Accenture saying that by the year of 2035, they think that the annual economic growth rate will double because of the use of AI. That is quite much, actually. And I think there are three main reasons why AI is growing so fast right now. One of them being improvement in machine learning methodology. And as me and my colleagues at the university do work on doing every day. But I don't think this is the main reason. For a lot of these systems that are in use now or algorithms were developed already in the 1980s, 1990s, and even in the 1970s. So I think a more important reason is, of course, high-speed calculations. We have computers that are able to process data much faster now. And also, as you see in the image, we actually have quantum computers coming more and more stronger as well. But I think maybe the main reason why AI is growing so fast is the availability of data, because we have so much of it now and we didn't before. Actually, I just heard that for every year that goes by, we actually double the amount of available data, meaning that in 2019, we created as much data as all of the years up to 2019. That's quite insane. That's quite an exponential growth, I would say. So we have AI systems coming and growing, but unfortunately, a lot of these systems are regarded as black box systems, meaning we know what goes into the systems and we know what comes out, but we have no idea what's going on. We know what kind of data puts in. We know maybe like a prediction or a decision or a classification. We know what comes out, but we don't know why. And that is what is a black box system. And this is why methods for creating explainable AI has attracted increasing attention these last years. For example, the national strategy for AI for Norway, it came out now in, I don't remember when, sometime in the spring. And I went down to the website and see what is important about this strategy. And I saw that on the front page, they had these bullet points. And they said, like, all over the place, we need ethical principles, we need human rights, we need responsible AI, we need trustworthy AI. And we see that people are really caring about making sure AI is responsible. And that is why I'm not going to show you a bit what a black box system is, because I guess a lot of you know. And I think the most common example of a black box system is a neural network. And I'm going to take quite briefly to talk how it works. If someone you don't know, you actually see a neural network here on the left side. It consists of an input, one or more hidden layers, and then one output. And the output could be some kind of prediction we want. Maybe we want to predict if a person is a man or a woman based on a few input data. For example, a person's height, a person's weight, or a person's age. And how the system works, or the neural network works, it takes the input and goes to a node, and the node just calculates linear combination of the inputs. For example, 2 times your height, 3 times your weight, and 1 times your age. Quite simple. And then what happens inside the node is that it takes this combination and makes it unlinear with some sort of unlinear combination function, like the sigmoid function. And then again, the output just take linear combinations of the node again. For example, 4 times node 1, 3 times node 2, 3 times node 3, etc. So that is basically a neural network. Now we all know how it works. It's not more difficult than that. And the problem is that this is also a neural network. And you can see already now that it's quite difficult to see how the yellow inputs are connected to the orange outputs, which strings are going where, how strong these strings are, everything. And also this is actually a quite easy neural network, because neural networks can have thousands of layers and you can have thousands of nodes. And we can easily see it's quite fast that it's not possible for us humans to comprehend what's going on. We do have black box systems. So then what on the other side is explainable artificial intelligence? To get you to understand this, I'm going to take you through one example. For example, we have an image of here a rooster, and then we want to classify this image with an AI system. What is this image? And so we take this image through a black box system, and we get the prediction, this is a rooster. And then we have the image, we have the prediction, but we have no idea what's happened in between. And if, for example, got the prediction beer, we would have no idea why the system failed, but now it worked luckily. So here enters explainable artificial intelligence, because what it does is kind of, you can add it on top of all black box systems. You can add it on top to first do the prediction and then try to explain why did this prediction happen. So that's exactly what explainable artificial intelligence does. It tries to kind of penetrate the system and see what happened, and then it will try to give us an explanation that is very easy for us humans to understand. So these heat maps are very popular. Here we can see that the system tries to tell us why the AI system thought this was a rooster, and we can see it was the red part of the head and the comb of the rooster, and that makes sense, right? So now we went from having no idea why prediction happened to getting some idea why the AI system thought this was a rooster. And I want to give you a few reasons why it's so important that we continue to create this explainable AI and not only black box AI. And I think one of the main reasons is improvement of the system, that we need to understand the AI system's weaknesses to improve them and find and change flaws and biases. And I think this part with biases are especially important because we have a lot of biases in our society. As the thing that I mentioned in the beginning, we might think that a person with a foreign name might not do as good a job. And we might think that it's not as important that female person survives. So this is a thing that biases that we might have in a society, and we don't want them. And we at least don't want to transfer them to a machine that's going to do some decision making for us. But the thing with AI and machine learning is that they are very good at trying to find patterns in the data, because that's what they created to do. And biases in data is a kind of pattern. So AI systems are good at finding these patterns and using them and even enhancing them. So one good example where this happened was a research study at the University of Washington. They had a lot of images of people in different kind of situations. And then they found out that the data was biased in a way that if there was a person in the kitchen, it was 33% more chance that this person was female. And what happened was that the AI system or the machine learning system picked up on this pattern and even enhanced it, thinking that if a person was in the kitchen, it was 68% more chance that this person was female. So only there we can see, there was maybe not as bad, it's like bad example, but at least you can see how easily it can pick up on these biases and actually use them when we don't want them to be there. Another important thing is verification of the system. Like there are a lot of applications where we cannot trust a black box system by default. Imagine, for example, going to a doctor, and then unfortunately the doctor will say, you have cancer and we have to treat you. And you can say, why do you think I have cancer? And they would answer, we don't know. The AI system told us so. Of course, we can't trust that. And then they start giving treatment without knowing anything more. Of course, we can't do that. So there are so many applications where we need to verify that the system works as intended. Also, learning from the system is very important because AI might observe patterns that are there that we humans don't see, but we want the AI to find it. That's often why we create AI, actually. And if AI learns something that we don't know, we humans want to know it as well. For example, I guess some of you heard when the first AI system beat the leading champion in Go, the Japanese game. And what happened was that the AI system actually used a new strategy that no one has ever seen before. And it won. So people started learning this strategy and people started using it. So then humans learned from an AI system how to play the Japanese game of Go. That's really cool. And the final reason, I think, also is a very important reason. That's the compliance to legislation. We have to make sure that our AI systems follows the laws and morals and rules of our society that we have to follow as well. And if we use black box systems, we will not know if the AI system actually follows our laws. An example where they on purpose tried to trick a system and found out that it worked very easily was a research in the United States where they tried to create an algorithm that will say if people should get a loan or if people should not get a loan in banks. And they made sure not to give any information that was illegal. So no information about gender, no information about race, etc., just legal information. And then started trying it out, and that it said you should get a loan, you should not get a loan, etc. And then they used Explainable AI to see why does it give these decisions, why. And then they found out that the variable that was really important was zip code. Actually, so they were like, why is it so important to see where people live? Why is that an important factor? And then you might know that in the United States, in some of the big cities, they have this kind of clustering of people with the same kind of ethnicity or race, also called kind of ghettos. So they found out that the AI system used this zip code as kind of a surrogate variable for ethnicity. So it did something illegal. And if there was a black box system that didn't open up, they would never know that. So now I hope you all have understood some reasons why it's important that we start creating explainable artificial intelligence. And I'm going to go through my favorite method for doing this. It's called layer-wise relevance propagation. And what's really cool about this is really cutting edge. This is state of the art within AI, and it's really cutting edge research that you're learning about now. So I think it's really cool that I'm here to be able to present this to you. So how LRP works is that you need a normal black box system, for example, a neural network like this, where you have some inputs and you have one output, same as earlier, maybe height, etc. And you want to classify if this person is a man or a female. And then you compute it using normal, putting a lot of data into it, and then you want to make a prediction. And then prediction might be this: I think this person is a man. And then what LRP does, when you have the finished black box, you can kind of put in on top and try to penetrate it and solve kind of what's going on. So then it starts in the back, it starts in the output, start with the classification, and it gives it 100% relevance. And then it distributes this relevance backwards into the system, using that kind of the connections between the nodes and the strength of the nodes. So you can see here, for example, it says that the upper node had a lot of relevance for this classification, the other two not so much. And it uses normal mathematical formulas to do these. And then again, it continues to distribute this relevance backwards into the system, now saying that the middle node was really important, the low node further down not so important. And then it goes all the way through the system, all the way to the end, and then we can see what kind of input was really important for this prediction to happen. And we can see that here x2 was really important, maybe this is height, so maybe you can then tell the persons watching the algorithm, you can say, we thought this person was a man because he was really tall. So then we went from not knowing why something happened to knowing a bit why you took this decision, and we can see, verify system, we can see that it follows our laws and rules, etc. So that was LRP. That is actually how you create explainable artificial intelligence. Of course, there are a lot of other also algorithms and methods out there, but this is at least my favorite and one of the few that has been proven not yet proven to be unstable. So I really like it. Some examples where it's used. I have seen it used in, for example, diagnosing of Alzheimer's disease. I can take an example here. We see that you scan someone's brain, and then they use a neural network or deep learning and black box algorithm to understand if this person had Alzheimer's disease or not. So they used this black box system, and we said it was 89% probability that this person had Alzheimer's disease. And maybe the patient said, why do you think so? The doctors would just say, we had no idea. The AI system told us so. Of course, it doesn't work. So that's when they put the LRP on top of it. And then the LRP showed them which parts of the brain were important for this classification to happen. And they could see that it was around the hippocampus that was really important. So the doctors know that the hippocampus is connected with Alzheimer's disease. So then they can verify, we think this is true. Then they can say to the patient that you have some changes in hippocampus area, so we think you have Alzheimer's disease. Immediately much more trustworthy, right? Another top area which is much been used is in classifying text documents. As we humans or people now create more and more text, both in social media, both in articles, and everything goes online, there have been more and more systems trying to classify text documents, reading a bunch of them, classifying them, putting in different cases. And for example, here we had the neural network saying that this text we think is sci-fi, we think it is about space. And as normal deep learning, we had no idea first why it would say so, but then enters LRP, and it kind of gives these heat maps telling us which words were important for this classification. So we can see it thinks weightlessness, astronauts, NASA, Earth, etc., made us believe that this was about space. And then we people can watch it and see, yeah, I agree, this makes sense. So that's it, some examples. And actually the last example here about text document, you can actually try creating XAI yourself. I have created quite an easy to do workshop in Jupyter Notebook. So you can go to my GitHub page, Ali Mead, and download it. And what you are going to do in that workshop is you're just going to enter any text that you want, and then you're going to use a neural network to classify the text, and then you're going to use LRP to explain why this text was classified as it was. So it's worth checking out. And then you can start creating explainable artificial intelligence, and then you can start making sure that the future of AI is more responsible, more ethical, and that follows the rules and laws of our societies. Great. Are there any questions, Håkan?
Yeah, so we have a couple of questions here. So one more there. We have you were talking here about, you had your examples was about deep learning algorithms, but what about traditional machine learning algorithms like linear regression or logistic regression? What kind of, do you have any explainable AI frameworks for those?
Yeah, the thing about this LRP is it works on very, very many kind of things, also support vector machines, and also I think it will work on linear regression. So we can use this on very much. But the thing is with normal machine learning, for example, linear regression and logistic regression often kind of have good explanations by themselves, good enough, at least I would say, so that it might not be as necessary. But yeah, I would think it would work, yeah.
Mm-hmm. And also, do you know, is explainable AI, is it mostly done in academia now? Is it mostly on the research stage, or is it used out in the industry?
Right now, I would say it's really in the research stage. It's really recently in years they have started making more and more of it. But I see that the development is going really fast. So I think it won't be long until they start using it also in business, the world. And I think they should, because I think the system are already quite good.
Mm. You mentioned a little bit about the legal system. Do you have any thoughts about, does the legal system, can it keep up with this new AI findings to integrate it into the laws, or how does that work? Do you have any views on that?
Yeah, I think that is a really, really, really good question. I actually I wrote a small paper about it because, as I said, the use of AI is growing so fast right now, and so I think it will be difficult to keep on starting using the laws, as the AI might go beyond the laws we have right now. So, but I think when I see at least the global world working together on things, for example, making strategies and making both the GDPR, setting those kinds of regulations, I think those are really positive signs that people are able to do things quite fast. So I'm positive, as long as I think the world needs to have focus on it.
And also, you, in this presentation, you were demonstrating the layer-wise relevance propagation, but what other types of method exists?
I think one of the famous one is sensitive analysis, SA, and kind of LIME is also one famous part. But what's kind of different with those is that they kind of explain not why a prediction was done. It more explains, difficult to say, it explains more what changed in the input will change the output the most. And that also kind of gives you something, but this LRP doesn't focus on change. It says what input had to say something on the output. So I think you get more information, not knowing how things changes, but knowing why exactly. So that's why I prefer this one. But of course, LIME and SA are also quite famous ones.
Mm. And then to our last question here, if people want to know more about this or want to contact you to get to know more, how can they contact you?
I guess also LinkedIn is good. Also, you can just, if you Google my name and University of Oslo, I think you will get my job email. I can also maybe post information in the chat if that helps, but LinkedIn and email will be nice.
Okay, thank you so much, Alise. So,
thank you.
So with that, I will introduce our next set of speakers. That is Manu and Malte.
Hello.
So Manu Gopinathan. Hello.
Hello.
So Manu is a machine learning enthusiast who works as a software developer for Knowit, and currently he's a part of a team tasked with building a new sales and ticketed solution for public transportation in Norway. And during his Master of Science studies, he specialized in artificial intelligence, and he did a thesis doing an extensive study on gender identification of authors. using deep learning and natural language processing. He's also one of the founders of Artificial Chapter, an initiative in Knowit for learning and sharing knowledge about artificial intelligence. And then Malte Loller-Andersen, he's a passionate software engineer and IT consultant for the Nordic consultancy Knowit, and currently he helps Vy optimize their prices on ticket sales. He spends his time writing code and is one of the founders of Artificial Chapter, Knowit's internal group for sharing knowledge related to artificial intelligence. And here he has been occupied with organizing summits and workshops, in addition to holding presentations about artificial intelligence.
That sounds about right.
So, welcome, and really great to have you here.
Thank you. Great to be here.
So what will you present tonight?
So we'll be talking about a couple of different reinforcement learning methods, which we used to train an agent to play Pac-Man.
Yep.
So we'll be explaining how reinforcement learning works through that, basically. So I'm just going to switch to my presentation now.
Okay, that's it. Yes, so the stage is yours, so looking forward to hearing you.
Sounds good.
Sounds good, thank you.
All right, so welcome to this presentation on reinforcement learning with Pac-Man. It's such a shame that we couldn't be there all physically, but as we've seen with the previous two presentations, we can enjoy great talks online as well. So we usually present this material as a 3 to 4 hour long workshop or a presentation, but obviously things are going to be a little bit different today. So today we're doing a compressed version, but that doesn't mean that we're going to talk really fast. It just means that we're dimming down on the details and only showing you the most fun stuff. So you guys can just sit back as we do most of the talking, and hopefully you can take away something useful. So let's take a look at the agenda. So we're going to start out with a brief introduction to reinforcement learning, explaining terminology and concepts with a few different examples. So even if you have no experience with this from beforehand, you will be able to follow along. The first model that we will be using is called Q-learning. We will explain what that means before showing an agent in action. The second model will be based on deep Q-learning, and this means Q-learning with neural networks. Now, Håkan gave us a great introduction, but let us tell you a little bit about ourselves before we begin nevertheless.
Yes, so my name is Malte. I'm currently working at Knowit, a Nordic consultancy firm, like Håkan said, and I've been working there for the last 3 years. I started working there directly after doing my master's thesis at the Norwegian University of Science and Technology, where I focused on artificial intelligence. And right now I'm on a project at Vy, where we use machine learning for various tasks.
So my name is Manu, and for the past few years I've been following the same path as Malte, really, because I've been working for Knowit as well for the past 2.5 years. And currently I'm outsourced to NNUG, a government-owned transportation company in Norway. And as mentioned earlier, they're trying to collect all the sales and ticketing solutions for public transportation in Norway to a single application, making it possible to travel anywhere in the country from this one app. So it's very ambitious and it's very cool. And also before working for Knowit, I did my master's thesis within machine learning at the Norwegian University of Technology, doing natural language processing on tweets to predict the gender of authors with a varying degree of success, I guess. All right, so I'm going to hand this to you, sir.
Thank
you. Get
you.
out of your way for now.
Thank you. All right, so what is reinforcement learning? So reinforcement learning is one of the 4 subfields of machine learning. And in machine learning, the algorithms are dependent on data and is not explicitly programmed to solve one single task. For instance, a neural network that Alise already talked about today, it can kind of learn anything as long as you feed it the correct data. So the same is true here for reinforcement learning. But reinforcement learning also has another thing about it, and it is that it creates data sets on the fly. Usually, the other subfields of reinforcement learning, you have to gather data and pre-process it before you can use it. But in reinforcement learning, you create data on the fly while you are training your algorithm. It has had a lot of hype the recent years, and it's used a lot in games that also was mentioned earlier. For instance, in Atari, Shogi, Go, Chess, Dota, StarCraft, and so on. But these games are just kind of a stepping stone before going out into the real world. And reinforcement learning is also used in fields such as medicine and finance, and as we saw the first talk today by Monica, also in recommendation systems in the Azure Personalizer. So before we continue, we kind of need to introduce 5 terms here. The first one is the agent. So the agent is a unit that performs actions. So for instance, in the Pac-Man game we're going to show you, it's going to be Pac-Man himself. An action is something that the agent performs into the environment. And it should be noted that an agent has a possible set of actions. So for instance, an action in the Pac-Man game is for the Pac-Man to either move to the left, right, up, or down. The third term is the environment, and that is the world through which the agent moves. The environment takes the agent's current state and action as an input, and then will output the agent's rewards and the next state that the agent is in. It's often, so they have states. A state is a concrete and immediate situation where the agent finds itself, and it puts the agent into a relation between enemies and rewards and so on. It is often a function of time, so you can kind of think about it like if you stop time, you are in a given state. And lastly, there is the reward, which is the feedback by how we measure the success or failure of an agent's actions. So for instance, when Pac-Man runs around on his map, we know when he picks up gold coins, that's probably a good thing, so he should have a positive reward. And when he gets caught by the ghosts, and he dies, it's going to be a negative reward. So it's going to function a little bit like this image right here. If we start on the left, we have the state and a reward. This is fed to the agent, and based on this, the agent makes a decision to perform a certain action. This action is performed into the environment, and the environment spits out the next state and reward for that action. This then continues in a loop until you reach a terminal state. And the terminal state in Pac-Man could be, for instance, when he wins the game or when he loses the game. Yes. This is a screenshot of the game we're going to show you. Just wanted to show you so you don't get confused the first time you guys see it. It's custom made by one of our colleagues here at Know It. And we have the Pac-Man at the middle bottom here, the guy with the gray guy with the stick. And then you have the ghost in the top right corner. And then you have all the bricks where you can't move. And then you have the gold coins that you have to pick up all of them, and then you win the map. And we're now in a given state, right? We're in a given state. You have the Pac-Man, the agent, the environment is the map, and you have the ghost in the top right. In order to move to the next state, you have to choose an action. And when you choose an action, you can then go to the next state. So it's going to look something like this. We can see here that the Pac-Man didn't move, but the ghost moved one to the right. And that means that Pac-Man either chose to move up or down. And because there are bricks there, he's just going to be standing there by himself and not moving. And with that, I think we're going to go to our first algorithm of today, which is Q-learning. And you can get this one.
Thank you. All right. So hopefully you now have a basic understanding about what reinforcement learning is about. And now I'm going to get more into how Q-learning works before showing you an agent trained using this knowledge. So what is Q-learning? Q-learning is an algorithm which learns Q values for state action pairs in the environment. Now, what does this mean? Well, for each possible state, there are a set of actions, and for each of these actions, the agent will learn a Q value. So a Q value is a measure of the utility or the quality of an action in a given state. It's a measure of how good it is, essentially. So when you have a fully trained model, the agent will perform the action with the highest Q value for the state it is in, because this is the action that would provide the most happiness for the agent. So in this figure, obviously, the agent would pick the action to go right because it has the highest Q value. Now, I like to explain Q-learning even further by providing a sort of relatable example, but this whole pandemic thing sort of ruins the setting of my example. So let's just for a second assume that COVID-19 just never happened, and let's say that you find yourself physically in Oslo at the Global AI meetup. And let's say that smiley face, that is you in square 0. Now, after a long day of workshops and talks, you're really looking forward to having a drink with the great people that you've met at Global AI. So you're going to try to get to the bar in square 8. Now, let's assume that you've never been to Oslo before and that you don't have a map. So you're going to roam around these squares until you find the place. And to be able to learn from your mistakes and also your correct actions, we have a measure for success, namely rewards. So what kind of rewards do we have here? Well, we have the bar in square 8, and this gives you 20 points. Then on the way, you could end up having food at the food court, which would provide 5 points, because it's always better to drink after eating food, right? Never drink on an empty stomach. If you're very unlucky, you could end up in the river, and that's minus 20 points. Additionally, we have a move penalty of minus 1 point. And the reason for this is that you're really thirsty and you just want to get a hold of that drink as quickly as possible. You don't want to roam around the city taking detours. You just want to get there as fast as possible. And because practice makes perfect, you will try to find this bar a certain number of times, and each of these tries will be called an episode. Squares 4 and 8, they're called terminal states. This is where an episode ends, and you will start again from the beginning. Now we will keep track of the Q values for each action in each state using a dictionary. We'll start out with an empty dictionary for each state, which means that all the Q values are initialized to 0, indicating that you don't really have any knowledge about the map. Then following the execution of an action, the Q value for the action that you picked in that particular state needs to be updated with the new information gained in the next state. And for doing this, there is a specific formula. There is a specific formula for doing this based on current Q values in the state you were in and the state you ended up in, and also the reward received in the next state. But I'm not going to get into the details of how this formula is set up for now. Just know that there is a formula and it's based on known values. So let's do a kind of a test run to see how the training process looks like. So in the beginning, you don't really have any knowledge about the maps. You're just going to pick a random action, and then you might end up in state 3. And following that, you need to update the Q value for going to state 3 from state 0, which you can see here as well. And then this will continue, and you might end up in state 6. And here you can see that the Q value for going to state 6 from state 3 is positive, indicating that something positive occurred when you did this. Because here you got to the food court, right? Compared to previously when you just got a move penalty. And then this will go on. And at some point you will end up in a terminal state. And when you do that, you will go back to the beginning. And here you can see as well that the magnitude of the Q values really reflect if anything positive happened when you chose those actions in those states. So the training process continues like this. It will go on for many, many episodes. And when you hit a terminal state, you will go back to the start. And then at some point, the model will converge, the Q values will converge to a point where the path to this particular bar is as clear as it can get. And this is essentially what we're going to do with Pac-Man, though Pac-Man differs a little bit. The general idea is the same, but it's also more dynamic. So you have a grid-like board with different states, but the states also depend on multiple entities because you also have these ghosts trying to chase down the Pac-Man. And you also have these dots that the Pac-Man is picking up along the way. So for this project, we used Python, which is very common for machine learning projects. For the deep learning part, we used Google's TensorFlow library. And we also used Keras, which is a wrapper around TensorFlow, making it a little bit more user-friendly. TensorFlow has actually improved a lot when it comes to user experience lately, but at the time, back in the day, it was very useful to use Keras. We also used Microsoft Azure's virtual machines and GPUs to aid us along the way. And we also made use of Jupyter notebooks through the Jupyter Hub when conducting workshops. All right, so with that said, I think I'm going to head into my IDE here and show you the agent in action. All right, so it doesn't really matter if the code is very small and difficult to see here, because I'm not going to get into the code specifically. I'm just in here to run the models. And what I'm going to do now is Malte already showed you how one of the maps look like. So I'm going to run that map and just have the agent pick random actions, just to show you how it performs when it hasn't really learned anything. So what's going on here is that the Pac-Man is just picking random actions, and as you can see, it's very bad. It loses pretty quickly, and I just want to show you that it's not possible to win this map by just picking random actions, even though it's a small map. All right, so when the Pac-Man gets caught 3 times, the game exits, indicating that it lost. So I'm going to show you how it performs when trained with Q-learning for 1,000 episodes. So here we can see that the Pac-Man goes to the right away, and then goes for most of those dots. And then it got caught once by the ghost before it went for the remaining dot. And sometimes we see like different tendencies. Like here we can see that the Pac-Man is kind of probing, trying to go to the right, but it's not able to go there because the ghost is there. And then when the ghost tries to chase it, it straight away turns around and goes in the opposite direction to get the dots. So clearly it has learned that getting caught by the ghost is bad, picking up those dots is a good thing, and then it combines this to win the game. Now, this map was very small, so I'm going to show you a slightly bigger map. And this map is bigger, so the model is bigger as well, so it takes a little bit more time to load the model. But let's see what happens here. So what we're going to see is that it's not really going to be performing very well. This map is a lot bigger. And you'd think that to perform better, we need to train it for more episodes. But as I'm going to explain, that's a little bit more problematic than it may seem. So I'm just going to head back to the presentation because it's not really going to be performing well on that map with Q-learning. So I'm just going to head back here. All right. So in the first map, there are 12 legal positions for the Pac-Man and the Ghost, and this approximates in around 4,000 possible states. And this is a very manageable number. On the other hand, the second map consists of 68 legal positions, and there are also 2 ghosts, and this, along with the 50 dots on the map, results in 2.7 into 10 to the 21st possible number of states, which is a pretty huge number. The problem with Q-learning is that it doesn't really scale as the number of states increase. And when you try training a larger number of episodes, trying to explore all these possible states, the model becomes very big, and it essentially becomes impossible to load into memory. And this is why we need something like deep Q-learning, which handles this problem in a much better way. So I'm going to hand it back to Malte, who's going to explain this to you.
All right, thank you, Manu. So since it doesn't work with this spreadsheet approach of the Q matrix, we have to introduce a neural network. And this is called the Deep Q network. In order to achieve that, we have to do 2 things. We have to replace the Q matrix with a neural network, as I just said, and then we have to add something called experience replay, which I'm going to explain in a minute. So it's going to look something like this. It looks familiar to the other one I showed you guys earlier. If we start on the right here, you have the environment, which gives the reward and the observed state to the agent. The agent then maps the state into a neural network, and the neural network computes what the optimal action is in that state. And then you perform that action in the environment, and this loop goes on until the terminal state. So experience replay is a technique of training offline. Online training is when you make one step in Pac-Man and then you update the Q matrix. You take one step in Pac-Man and then you update the Q matrix. Then you take one step and update. This is online training. But what we can do instead, we can do something called offline training. This works as you take one step, and instead of updating, for instance, a neural network or a Q matrix, you save the experience, which contains all the information about the move. It contains the current state, the action that was performed, the next state, and the reward for it. So those 4 things. And you save it instead in memory. And then when you take a lot of steps, you'll have a big data set, kind of. And then you can take that data set and then you can train on that one. This is good because neural networks or deep Q networks, they usually tend to forget early runs. So let's say that you're in the early game of a map and the agent learns how to beat that. But then when you get into the mid game, when you're training on the mid game, it'll forget how to properly do the early game. So when you have this bank of experiences, you're going to have both from the early and mid and late game, and you take random samples from these, so you're sure that you're training on all early, mid, and late game scenarios. And then it's also nice just to learn one experience multiple times because it's saved, so you can learn it multiple times. Because neural networks, when they update their weights, it's just a very slight change to these weights, so you have to learn it multiple times. Another thing you need to do is to map a state to a neural network. And neural networks, they need numbers as inputs. They can't just take like an object in a programming language. So for this, we use one-hot encoding. It looks something like this. What we do is that we take a string representation of the map, and then we just loop over and we concatenate certain vectors to it depending on what kind of tile it is. So I'm just going to show you guys an example here. If we take the bottom left is a string representation of the level 0 map that we showed you the first, where the P is Pac-Man, G is Ghost, and the dots, those are the coins. This then, you loop over this one and you get a certain vector. And this vector is true only for exactly that state. You put this vector, this is going to be the input layer of the neural network, and you put this, you let the neural network train for a little bit, and it's going to give out 4 values, each value for one of the 4 actions. So it's left, up, right, and down. And if you want to take the optimal choice, you take the action with the highest value. So I'm going to show you guys how it can beat the level 2 using a deep Q network. So let's see here. We're going to run with the model. So this is trained after 4,500 episodes, which means that... How did you comment out on your...
Command 8.
Command 8, it's good to know. Okay, so we're gonna run this. How did you run again?
Control R.
Control R, all right.
I have like a special setup.
Yeah, we got a special setup. So we can see now that the Pac-Man trained for about 26 hours on an Azure virtual machine. I don't remember which one. It's maybe a little bit unfortunate, but it's going to be able to solve this level 2 that we're showing you guys. So you can see that at first it kind of had learned to rush to the mushrooms because they're really high value. We have assigned them a high reward. Then it's going to finish one side of the board up, and then it might suicide because then it gets teleported into the middle again, and then it's going to run to the other side and finish the map. So we are pretty happy with how that turned out. We have more maps too, but I don't think we have time today to look into them, unfortunately. Let's see here. Yes, so some improvements that you can do with this. Exploration, it was Monica briefly mentioned it, but when you do exploration, you want to make sure that all of the possible states are visited, and you want to visit a broader set of them in the beginning. So you should have a high exploration in the beginning and then lower it as the agent learns. You should also try to use convolutional layers. They're usually they're usually pretty good at 2D inputs, so they're often used in images and stuff. But Pac-Man is also a 2D space, so you can kind of take advantage of that. Then there's the obvious one, which is more training time, more memory, and more processing power. And then the last real improvement that you can do to this is to prioritize experience replay. Instead of taking random samples from it, you can kind of tell, okay, my agent is not performing so well in this mid-game, so we're going to take more experiences that are mid-game related. And I think that is about it. Yeah, so if you guys have any questions or anything, we can take that now, or else you can also reach us at our Twitters, Real Manu Gopinathan and Real Malte. Yeah, thank you guys.
Thank you so much for a very interesting presentation here. So we have a couple of questions.
Yeah.
So one question here is about reinforcement learning in general, because now you showed how it can be used in games. And would you say, is that a typical use case, or is there other types of domains where reinforcement learning is used?
There are definitely a lot of more domains where it's used. I briefly mentioned it, but in recommendation systems, they're quite widely used. And Monica, in the first talk today, she was talking about reinforcement learning in the Azure Personalizer. They're using reinforcement learning to provide better content for purchasers at websites. They're also used in medicine to diagnose cancer based on images.
Which was also mentioned in the second talk.
Yeah, it was. And then it's also used in finance, where trying to predict financial markets.
And another one of our viewers wanted to know if reinforcement learning, is that what used to be called agent-based modeling?
Yeah, so they can be maybe a little bit confusing, I see. So kind of reinforcement learning is about training an agent and make it learn how to solve a specific problem, while agent-based modeling is more like understanding the effects of multiple agents, how they interact with each other in an environment. Usually agent-based modeling is a little bit more about finding like simple rules or better understanding for a reason for particular outcomes, instead of actually training an agent to solve a problem. Yeah.
And also, I think the last question is how much time and what type of configuration did you use? Because you mentioned that you did some training on Azure.
Yeah, so when you talk about configuration, you mean like the size of the neural network?
Or do you mean like the GPU?
No, I think it was more about the GPU and...
Yeah, it is one of the larger ones. I don't know if you remember which one.
I don't remember the exact details, but it wasn't like the stock one that you can choose. You can choose between a lot in Azure, actually. So you have some GPUs which are pretty cheap to use, and then you have some larger ones which cost a little bit more. But I don't quite remember the exact one.
It had something about
C24.
Yeah, it had like 24 CPUs, and then it had 2 GPUs, if I remember correctly.
Yeah, I think so.
Unfortunately, we don't remember that. It was quite a while ago we trained this. Yeah. Okay.
Okay, so really great presentation here. So now, to finish our evening, I will call the other speakers up here on stage. So we'll add Alise and Monica, like this. So do you have any final words here to our viewers?
Thanks for coming.
Monica? Yep.
Thanks for tuning in, guys. It was a pleasure. I wish you could meet you guys in person, but I guess we'll have to wait until next year. Yeah.
Yes. Hope to see you in another occasion.
Yeah. Yep.
So on behalf of the global AI community, I just want to thank all of you for making this effort. It was really, really great. And this will also be saved in our YouTube channel, so people can watch it afterwards. And as I mentioned before, we will finish this off with just showing this slide with the Azure Heroes Summer Learner badge. So with that, I thank you all and wish you all have a great evening.